Okay, so picture this. You're walking down the street, right? Buildings towering all around you, sun hitting a window just so. You might not think about it much, but it's all lines and angles. And that's kind of wild when you realize it. Like, that's the basis of everything from, I don't know, a simple hut to, like, the craziest skyscrapers.
It really is. You're totally right. What seems super basic is actually like the blueprint of how we experience space, how we build, how we understand the world around us.
It's pretty mind-blowing when you stop and consider it. And speaking of mind-blowing, that's exactly where we're headed today. You shared a chapter with me that gets right into lines and angles, really breaks it down. And our mission, well, it's kind of like we're on this treasure hunt to find those golden nuggets of insight, those relationships that make everything else click. And we want to do it without getting bogged down. Like we want the good stuff, clear and concise. Think of it as our super efficient guide to lines and angles.
You like that analogy. And the source material is set up perfectly for that. It starts with all the core definitions, and then it builds up step by step to these like really important theorems about how lines work, how they intersect, how they act when they're parallel, all that. It's designed to be very clear and easy to follow.
Awesome. So let's dive in, starting with the basics, right? Line segments, rays, and lines. Now, something I noticed right away is the chapter uses that same notation for all three, like AB. At first glance, I was like, huh, isn't that a bit, I don't know, vague?
Yeah, it seems that way, right? But the interesting thing is they actually rely on context. So, like, the symbol's the same, but whether it means a segment with two ends, a ray going on forever from one point, or a line going forever in both directions, you figure that out from where it shows up, in the problem or in the explanation. The information around it makes it clear. I think it's actually a pretty clever way to show how those ideas are connected without getting too hung up on symbols early on.
I see. Yeah, it's kind of like a word that has multiple meanings, but you know which one it is from the sentence. Makes sense. Okay, moving on, we've got collinear and non-collinear points. Pretty straightforward, right? Basically, if they're on the same line, they're collinear. If not, then they're not.
Exactly. You got it. If you can draw a single straight line that goes through three or more points, boom, they're collinear. If you can't, well, then they're just hanging out in their own space, non-collinear.
Easy peasy. And then we have the star of the show, the angle itself. Two rays shooting out from the same starting point. We have our two sides or arms and that central point where they meet, the vertex. And then comes the whole gang of angle types. Acute, right, obtuse, straight, and reflex. Feels like a good old review, but nailing down those degree ranges, that's super important as we move forward, wouldn't you say? So just to recap, acute is less than 90. Right, is exactly 90.
Oh, absolutely. Knowing those degree ranges, that's a key. Like really understanding that an acute angle is smaller than a right angle is that perfect corner, an obtuse angle is wider than a right angle but not a straight line yet. A straight angle is flat, 180 degrees, and a reflex angle, that's the one that swings past 180 but hasn't made it all the way back around to 360. Those are like our building blocks right there. And we can't forget complementary angles, those buddies that add up to 90, and supplementary angles, the pair that make a straight line, 180. We're going to be seeing those guys a lot.
For sure. So now we've got the individual angles down. Let's talk about how they relate to each other, especially when we get to adjacent angles. The definition here is pretty specific, right? They share a vertex, they share one arm, and then their other arms, the ones that aren't shared, those are on opposite sides of that shared arm. Figure 6.2 in our material shows this really well.
Yeah, it's all about that shared boundary. And what's really important about adjacent angles is they work together, their measurements add up. So like the measure of two adjacent angles put together, that's equal to the measure of the big angle formed by those two outside arms. If we think about, let's say, angle ABD next to angle DBC, the whole angle ABC, that's just those two smaller angles added up.
Right. The chapter also makes it clear when angles are not adjacent, which is super helpful. Like if those non-common arms end up on the same side of that shared arm, nope, not adjacent. It's all about where those sides are hanging out.
Exactly. It's a small detail, but it can really save you from getting mixed up later, especially when we start looking at what happens when lines cross and all the different angles that pop up.
Which brings us to a super important type of adjacent angle, the dynamic duo, linear pairs. So what makes a linear pair so special?
Well, think back to figure 6.3. A linear pair, it's like adjacent angles on steroids because their non-common arms form a straight line. And because they make that straight line, those two angles always add up to 180 degrees. That's a rock solid fact. And a lot of other geometric ideas build right on top of that.
I love how it all connects like that. Now, let's think about two lines just chilling on a plane. They've got two options. They can cross path at one point, or they can just keep going forever without ever meeting. Those are our parallel lines, and figure 6.5 shows us what that looks like. And the chapter points out something cool. Parallel lines always keep that same distance between them, no matter how far they go.
Yep, that constant distance, that's like their signature move. But when lines do intersect, things get really interesting.
That they do, and that's where vertically opposite angles come in. When two lines cross, they make two pairs of these angles, like right across from each other at the intersection point. So in figure 6.4, we can see angle AOD and angle BOC. That's one of our pairs. What about the other one?
The other pair, let's see, that would be angle AOC and angle BO. They're the ones staring each other down from across that intersection. And this is where theorem 6.1 drops some knowledge on us, those vertically opposite angles. They're always equal. It sounds simple, but that little fact is super powerful because if you know one of those angles, boom, you know all four. It's like a cheat code for solving geometry problems.
Right, it's like a shortcut. And the best part is, the chapter doesn't just tell us this, it shows us why it's true. And the proof. Well, it all comes down to linear pairs, those buds we were talking about earlier. Remember how we said they always add up to 180 degrees? Well, watch this. Let's say we've got lines AB and CD. They're crossing at point O, like in figure 6.8. Now, the ray OA, it's sitting on line CD, and that makes a linear pair. Angle AOC plus angle AOD equals 180.
And we can do the same thing with ray OD hanging out on line AB. Another linear pair pops up. Angle AOD plus angle BO equals 180. Now here's the magic. Remember, in logic, if two things are equal to the same thing, they're equal to each other. Well, that means angle AOC plus angle AOD equals angle AOD plus angle BO. And if we get rid of angle AOD on both sides of that equation, what do we get? Angle AOC equals angle BO. Boom. We just proved that one pair of vertically opposite angles is equal, and the same logic works for the other pair, angle AOD and angle BOC.
So that idea of linear pairs, those adjacent angles making a straight line, that's the key to understanding why vertically opposite angles are always equal. It's like a chain reaction of logic.
Exactly. That's what makes geometry so cool. One idea built on another. It's like this amazing structure built on pure logic. And this proof shows how those basic truths, like the linear pair, connect to these more advanced ideas.
Speaking of basic truths, let's talk about the linear pair axiom itself. Axiom 6.1, it states that if you've got a ray chilling on a line, those two adjacent angles it makes, they'll always add up to 180. Figure 6.6 shows this perfectly.
It's like the official rulebook for linear pairs, right? But then the chapter throws us a curveball. It asks, what about the other way around? If we have two adjacent angles adding up to 180, do their outside arms always make a straight line? That's what statement A is all about.
And figure 6.7, it shows us a few different scenarios. It looks like the only time those arms line up perfectly straight is when the two angles actually do add up to 180.
Exactly. And that leads us to axiom 6.2, which says, yep, the reverse is true too. If two adjacent angles add up to 180, those outside arms are going to form a line. No doubt about it. So we've got these two axioms, and together they're the linear pair axiom. It works both ways. It's a two-way street. You know, if a ray is on a line, the angles add to 180, and if the angles add to 180, those arms make a line. It's powerful because it lets us go back and forth in our proofs.
Okay, let's put this all into practice. Example 1 gives us two lines, PQ and RS, crossing paths, and we know the ratio of two angles, angle POR and angle ROQ, is 5:7. We got to find all four angles. How do we even start?
Well, the linear pair axiom is our friend here. PQ is a straight line, OR is hanging out on it, so angle POR and angle ROQ are a linear pair, which means they add up to 180. We know the ratio is 5.7, so let's imagine that 180 degrees is like a pie cut into 5 plus 7, that's 12 slices. Each slice would be 180 divided by 12, which is 15 degrees. So angle POR, it gets 5 slices, 5 times 15, that's 75 degrees. And angle ROQ snags 7 slices, 7 times 15, 105 degrees.
And to find the other two, angle POS and angle SOQ, well, the vertically opposite angles theorem comes to the rescue. Remember how those are always equal? So angle POS, it's across from angle ROQ, so it's got to be 105 degrees too. And angle SOQ is across from angle POR, making it 75 degrees.
Perfect. We use two big ideas, the linear pair axiom and the vertically opposite angles theorem, and just like that, we cracked the code. We know all four angles.
Like a puzzle, and we found all the pieces. Okay, next up, example 2. This one introduces angle bisectors, basically rays that cut angles in half. We have OS on line POQ, and then OR and OT, they're the bisectors of angle POS and angle SOQ. We know angle EOS is X, and we need to find angle ROT.
All right, let's break it down. OS is on line POQ, so angles POS and SOQ are a linear pair, meaning they add up to 180. We know POS is X, so SOQ has to be 180 minus X. Now, OR bisects POS, meaning it cuts it in half. So ROS is X divided by 2, same thing for OT and SOQ. SOT is 180 minus x divided by 2, which we can simplify to 90 minus x divided by 2.
Now, for the grand finale, to get angle ROT, we add ROS and SOT together. So it's x divided by 2 plus 90 minus x divided by 2. Notice those x divided by 2's, they cancel out, and we're left with 90 degrees for angle ROT. It's kind of cool. No matter what x is, as long as OR and OT are bisecting that linear pair, they always make a right angle. It's like a hidden rule of geometry.
It really is. It's those hidden rules that make geometry so fascinating. You start with these simple ideas, and they lead to these really elegant and predictable relationships.
Agreed. Now, example 3 throws us 4 rays, OP, OQ, OR, and OS, all coming from the same point, O. We have to prove that all the angles around OPOQ plus QOR plus SOR plus POS add up to 360. It's like we're going in a circle, literally.
I love this one. To prove this, we need a little trick, a geometric construction. We're going to extend one of the rays, let's say OQ, back through point O to make a straight line, TOQ, like in figure 6.12. Now, look at line TOQ. Ray OP is standing on it, making a linear pair. Angle top plus angle POQ equals 180.
And we could do the same thing with ray OS. It's also on line TOQ, making another linear pair. Angle TOS plus angle SOQ equals 180. But wait, SAQ is actually made of 2 angles, SOR and QOR. So we can rewrite that second equation as angle TOS plus angle SOR plus angle QOR equals 180.
Exactly. And if we add those two equations together, we get angle top plus angle POS, TOS plus angle K, POS plus angle QOR. All that equals 360. Now here's the final piece of the puzzle. Top and TOS are next to each other, and their outside arm make up OP and OS. That means they form angle POS together. So we can swap those two angles for POS and bam, we get exactly what we wanted. Angle POQ plus angle QOR plus angle POS equals 360. It's like we pieced together a whole circle, degree by degree.
It's so satisfying when it all comes together like that. Okay, we've spent a lot of time with intersecting lines. Now let's switch gears to the lines that don't intersect, our good old parallel lines, and specifically how they behave when another line, a transversal, cuts across them.
Right. When a transversal crosses 2 or more parallel lines, it creates all sorts of interesting angle pairs. We won't dive into every single one today, but the source material does highlight one super important theorem about lines that are parallel to the same line.
Right, theorem 6.6 says if 2 lines are both parallel to a third line, they got to be parallel to each other too. It's like a friend of a friend situation. If you're friends with someone and I'm friends with that same person, well, we're kind of friends too, right? Figure 6.88 shows us visually what we're talking about. If line M is parallel to line L, and line N is also parallel to L, then M and N have to be parallel as well. It makes sense intuitively, but there's actually logic behind it.
It's like the transitive property, but for parallel lines. And the reason it works has to do with something called the corresponding angles axiom. And its converse, it basically says that if M is parallel to L, then any transversal will create equal corresponding angles. And if N is also parallel to L, that same transversal makes another set of equal corresponding angles. Because those angles are equal, M and N have to be parallel. It's all about those corresponding angles.
Okay, let's see how this plays out in real life. Example 4 gives us 2 parallel lines, PQ and RS, with a transversal cutting across them. We know angle MXQ is 135 degrees and angle MYR is 40 degrees. Our mission is to find angle XMY. And the solution is pretty clever. We basically draw in another line to help us out.
It's like a secret weapon, that extra line. So let's call it AB, and we're going to draw through point M, so it's parallel to PQ. If it's parallel to PQ, then by theorem 6.6, it's got to be parallel to RS as well. Now we've got 2 sets of parallel lines, which means we can use all those cool rules about transversals. Look at transversal XM crossing AB and PQ. We know QXM is 135, so XMB has to be 180 minus 135, which is 45 degrees.
Right, and then if we look at transversal YM crossing AB and RS, angles BMY and MYR are alternate interior angles, and those are always equal when you've got parallel lines. So BMY is 40 degrees, and finally the angle we're looking for XMY, that's just XMB plus BMY, which is 45 plus 40, giving us 85 degrees.
It's like we broke down this complicated problem into these smaller, easier to solve pieces just by adding that one extra line. That's the power of using those parallel line properties. It gives you tools to tackle anything.
For sure. Now, example 5 throws us another curveball. We've got a transversal AD crossing lines PQ and RS. But this time, it's the angle bisectors BE and CG that are parallel, and we need to prove that PQ and RS are parallel too. It's like we're working backward from the bisectors to the original lines.
Yeah, it's a little tricky. So we know BE and CG are parallel and AD is cutting across them. That means the corresponding angles have to be equal. So angle ABE, that's the one made by AD and BE, it's the same size as angle BCG, the one made by AD and CG. Now, because BE bisects angle ABQ, angle ABE is half the size of ABQ. And CG bisects BCS, so BCG is half the size of BCS. If half of ABQ equals half of BCS, then the whole angles ABQ and BCS got to be equal too. And guess what? Those are corresponding angles formed by AD crossing PQ and RS. If they're equal, then PQ and RS are parallel. It's like dominoes falling, one thing leads to another, and bam, parallel lines.
Wow, the parallel bisectors force the original lines to be parallel, too. It's all connected. It's beautiful.
I know, right? It shows how these geometric relationships all work together.
Okay, last example. Example 6. We've got a chain of parallel lines. AB is parallel to CD, and CD is parallel to EF. We also know EA is perpendicular to AB, making a 90-degree angle, and angle BEF is 55 degrees. We need to find angles X, Y, and Z.
All right, let's do this. First up, Y. We know CD and EF are parallel, and EDs are transversal. So Y and BF are interior angles on the same side, which means they add up to 180. That means Y plus 55 equals 180, so Y is 125 degrees.
Now for X, we know AB and CD are parallel, and EAs are transversal. The angle where EA meets AB, that's 90 degrees, and then we have X, those are also interior angles on the same side. So they got to be supplementary too. 90 plus X equals 180. That means X is 90 degrees. Wait a minute. I'm looking at figure 6.22 again, and I just realized something. X and Y are actually corresponding angles. AB is parallel to CD, and BE is crossing them. So X has to be equal to Y, which means X is also 125 degrees. Sorry about that, I got a little ahead of myself.
No worries, it happens. And you're right, X is indeed 125. Okay, now for Z, AB and EF are parallel too, because if AB is parallel to CD and CD is parallel to EF, then AB and EF got to be parallel as well. It's like that transitive property we were talking about earlier. Now, think of AE as a transversal. EAB, which is 90 degrees, and FEA, which is Z plus that 55 degrees, those are interior angles on the same side, so they got to be supplementary. That means 90 plus Z plus 55 equals 180. If we simplify that, Z plus 145 equals 180, so Z has to be 35 degrees.
Awesome, we found them all. We used all those rules about parallel lines, corresponding angles, interior angles on the same side, alternate interior angles, and even the transitive property. It all works together like a well-oiled machine.
And that's the beauty of geometry. It's this interconnected system of rules and ideas, and when you understand those rules, you can unlock the secrets of any shape or figure.
So to wrap things up, let's recap those big ideas we covered today. We drove deep into the linear pair axiom, that two-way street of a rule. We explored the vertically opposite angles theorem, those equal angles across from each other. And we tackled the idea that lines parallel to the same line are buddies. They're parallel to each other too. These concepts, they might seem simple at first glance, but they're the foundation of so much in geometry.
They're like the basic ingredients in a recipe. You know, you need them to build something amazing, and once you understand them, you can start to see them everywhere, in bridges, in buildings, in nature, everywhere.
I love that. So, listeners, next time you're out and about, take a look around. Notice the lines, the angles, the shapes. You might start to see those geometric principles at work, those building blocks we've been talking about. How do they all come together to create the world around us? From a simple chair to the most amazing skyscraper, those basic ideas are at play. It's something to think about.
And remember, this is just the beginning of your geometric journey. These ideas, these are your tools, your weapons, your building blocks. As you learn more about geometry, you see how these ideas pot up again and again. They're the foundation for understanding those more complex theorems and ideas you'll encounter down the road. Got this.